Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 43. In this lecture, we'll discuss torque. This topic is covered in chapters 10 and 11 of our textbook by Survey and Jewett. In our last few lectures, we've been talking about the angular motion of objects. We've been talking about angular position and angular velocity and angular acceleration. However, we have not yet talked about what makes objects rotate. We have not talked about the cause of angular motion or the cause of angular acceleration. That's the topic of today's lecture. Now, before formally answering that question, let's just consider a couple of hypothetical scenarios. In this particular scenario, we have a beam balance that is often used to measure the masses of objects. Basically, it consists of a horizontal rod that is pivoted at the center, and the rod is free to tilt to the left or to the right. In effect, the rod is free to rotate around the pivot point. At the two ends, we have two masses. So we have placed a 1 kilogram mass at the left end of this rod and a 1.5 kilogram mass at the right end of the rod. Obviously, gravity is pulling on these things, and so we imagine that there are forces acting on this rod. On the left side, we have a force that is pulling the rod down. We can calculate this force. This is just mg. But on the right, we have a bigger force that is pulling it down. It's also mg, but notice the m is bigger. It's 1.5 kilograms. So the question is, which way will the scale tip? And with any kind of basic intuition, most of you can probably guess that this scale is going to tip to the right, meaning that the right side is going to go down and the left side is going to move up. Here is a slightly more challenging scenario. So essentially, the same problem that we've been talking about, again, 1 kilogram, 1.5 kilograms, the same beam that is free to rotate around this central pivot point. But notice we have now moved the 1.5 kilogram mass in a little bit. So the 1.5 kilogram mass is no longer hanging at the end or at the tip of this rod. It's hanging maybe halfway in or something like that. And now it's probably a little more difficult for you to answer the question of which way this will tip. It should feel like on the one hand we have a greater force being applied on the right side, although that force is somehow less effective at causing this object to rotate. If I told you that the 1.5 kilogram object has been moved almost all the way in, very close to the pivot point, then most of you would probably guess that the scale would tip to the left. In other words, the 1 kilogram mass would go down. We want to make this intuition precise. We want to be able to calculate a quantity that tells us exactly which way the rod will rotate or which way the scale will tip. Clearly, it's not enough to just know the forces. Certainly, we can say that the rotation of the scale is influenced by the forces, so the magnitude of the forces matters, but the location of the force somehow matters as well. It matters whether weight is being applied to the middle of the rod or the right end of the rod, for example. So we'll develop a precise formula for the quantity that tells us exactly how this is going to rotate, but when we finally see that formula, we expect it to involve magnitudes of forces, but also somehow the location of forces, like how far away the forces are being applied from the pivot point. Here's another thought experiment for you to consider. This time, imagine you have a wrench and you're trying to turn a bolt. Maybe this bolt is stuck. Imagine it's a rusty bolt, and you're trying to turn this bolt using a wrench. The question is, which of these two forces is more effective at rotating the wrench? So once again, we're trying to bring about rotational motion. We're applying a force to the system, and we want to know which one of them is better or more effective at rotating the wrench and the bolt. The two forces that we're considering have the same magnitude, so the lengths of these arrows are the same, but one of them is being applied over here, a little bit closer to the bolt. This one is being applied farther away from the bolt. The axis of rotation in this problem is going to be the center of the bolt. We call that the pivot point sometimes. So the pivot point is the point around which everything is going to be rotating. So other points of the bolt and the wrench are going to be executing circular motion, and the centers of those circles will be at the pivot point. In this case, it turns out F2 is the more effective force. If you've never used a wrench before in your life, you might not have much intuition about this type of a thing, but it turns out in general, if you're trying to turn a rusty bolt, it is better for you to hold the wrench as far away from the pivot point as possible and then apply your force. Here's another scenario to consider. We're now going to grab the wrench at the end, but we have two possibilities. One possibility is to pull the wrench straight down, and the other possibility is to pull the wrench at an angle. And the question is, which one of these is more effective at turning this wrench? Remember, the goal again is to essentially rotate this rusty stuck bolt, and we want to know which one of these forces is better at turning this bolt. If you don't have any intuition about this kind of a thing, you might want to consider an extreme case. Imagine grabbing the wrench at the end and then applying a force parallel to the wrench's handle. So applying a force basically directly aimed at the center of the bolt, at the pivot point. If you grab the wrench and you basically push on it towards the bolt, you can probably see that you're not going to rotate anything. That kind of a force will be completely ineffective. Maybe that'll help you decide that F2 is actually the more effective way of turning the wrench. If you want to turn this wrench, you should grab it as far away from the pivot point, and you should pull it in a direction that is perpendicular to the handle of the wrench. All of this might not be obvious to some of you, so our goal really is to define a new quantity and have a formula for it so that we can plug in some of these numbers into that quantity, and hopefully this quantity will tell us exactly which is more effective. You'll see the formula in just a few minutes, but already you should be thinking that the parameters we expect to see in that formula, in this new magical quantity that we're about to define, are these. The formula should depend on the magnitudes of forces. Obviously, the more force you apply to the wrench, the more effective you will be. But the location of the forces is important, so it matters whether you apply the force to the middle or the end or very close to the pivot point. But also the direction of the forces matters as well. It matters whether you're pulling at 90 degrees or at 45 degrees or at 0 degrees. Somehow the angle or the orientation of these forces must show up in the equation for this new quantity that we're interested in. All right, so I just asked you to consider a few different hypothetical scenarios where you're trying to rotate an object or determine the rotation of an object. And it turned out that it wasn't always easy figuring out how an object is going to rotate. It turns out force by itself does not always answer the question, how will an object rotate? To answer that question, we need a new quantity called torque. You can effectively think of torque as angular force, although that's not a very common term. Its correct technical term is torque. Torque is the cause or agent of angular acceleration resulting from the application of a force to an extended body. So here in this picture, we have an extended body, that's the wrench. Remember, an extended body is basically any body for which the mass is not concentrated at a single point. Any object that basically has a length and a width and a height is referred to as an extended body. And to this extended body, you can apply forces. Here are several different forces that could possibly be applied to this wrench. And each of these forces, A, B, C, D, E, F, will have a varying degree of effectiveness in terms of rotating the wrench. Some of them might not be effective at all. For example, if you pull this wrench along vector C, then you're not going to be rotating it at all. You're just going to be removing it from the bolt. On the other hand, vectors B and E would be extremely effective, but of course they will rotate the wrench in opposite directions. In each of these cases, there is a torque, and the torque is exactly the thing that tells you how effective that force will be in bringing about angular acceleration. Of course, if you can cause angular acceleration, then you can change velocity, and if you can change velocity, then you can change angular position, and that's really what we're interested in when we're talking about the rotation of objects. So how do we calculate this magic new quantity? Well, torque is denoted by Greek letter tau, and tau is defined as R cross F. This cross is the cross product that we discussed in our last lecture. If you want to know how effective each one of these forces will be in rotating the torque, in rotating the wrench, you need to calculate its torque. For each one of these, you need to know what the force vector is. You need to know where it is being applied. So R is a vector from the pivot point to where the force is being applied. And then you need to calculate the cross product, and the new product that you get will tell you exactly how much angular acceleration you will achieve. Remember from our last lecture that the magnitude of a cross product is equal to the magnitude of the first item times the magnitude of the second item times sine of the angle between the two items. The two items I'm referring to are these two vectors, the position vector and the force vector. There's some angle between them. We will refer to that as theta. And of course, each one will have a magnitude. We're referring to those as R and F. And this particular product gives you the magnitude of the torque. Now, torque is a vector. Which way is it pointing? For this, you will need the right-hand rule, but remember that it will always be perpendicular to R and F. So earlier, when we were discussing the tipping of the beam scale, if you really want to know which force will win or which way the scale will tip, you have to calculate the torque for each force, and then the one with the bigger torque wins. Also, when we were talking about the rotation of the wrench and you wanted to know which force is more effective at turning the rusty bolt, you would have to calculate the torque for each one of those forces, and then the force with the largest torque essentially wins or is the most effective force. Note that our definition of torque embodies the three basic properties that we were talking about. Torque depends on the location of the force, so where you grab the wrench in order to pull on it. It depends on the magnitude of the force, so are you pulling with 100 newtons on the wrench or 200 newtons? And it also depends on the direction of the force, more precisely the angle between the position vector and the force vector. Keep in mind that torque is causing angular acceleration. And of course, angular acceleration corresponds to a change in angular velocity. So when you see torque in a problem, you should be thinking, oh, there's going to be some angular acceleration. And of course, that means that the angular velocity of the object or the system is going to change. And of course, that then means that the angular position could also change. And then we have studied a whole bunch of other equations, like the angular kinematic equations, that can tell you precisely how the angles are going to change. Note the similarity between torque and force. As I mentioned earlier, you can almost think of torque as basically angular force. So force causes linear acceleration, whereas torque causes angular acceleration. We will want to measure torque, so we will need a unit of measurement. The SI unit of measurement for torque is the Newton meter. That should make sense because after all, if you look at this formula, F is measured in newtons, R is measured in meters, and sine of theta is unitless or dimensionless, so torque is often measured in Newton meters. You might remember from our discussion of energy that a Newton times a meter is also referred to as a joule. So you can say that torque and energy have the same units. However, to distinguish them, we'll almost always use joules for energy and Newton meters for torque, although technically they are the same units. Let's do a practice problem involving torque. For each case, calculate the torque about the center of the bolt. So we have 4 scenarios to consider, scenario A, B, C, and D. In each scenario, we have a wrench and we're trying to basically turn or rotate a bolt. In each scenario, a different force is being applied in a different way. In scenario A, imagine you grab the wrench at one end and you apply a force of 40 newtons. And the angle is at exactly 90 degrees relative to the handle of the wrench. This force is being applied at a distance of 30 centimeters, so don't forget to convert that to meters. Calculate the torque in this scenario, and then similarly in scenario B, C, and D. Once you know the torque in each case, you will know exactly which one will be most effective and which one will be the least effective in turning the bolt. All of your calculations will essentially use the same formula. Remember that the magnitude of torque is going to be the magnitude of the position vector, magnitude of the force vector, and then sine of the angle between them. When I say the position vector, I mean the vector that points from the pivot point to the force. So in scenario A, R is going to be 30 centimeters, but in scenario B, R is going to be 20 centimeters. Here we're again grabbing the wrench at one end, so R is going to be 30 centimeters. Notice in all cases, the pivot point is the center of the bolt, but where the force is being applied could be different locations, so that's what the R vector is telling us. We're also interested in the angle between the R vector and the force vector. Remember, to calculate the angle between two vectors, you need to put them tail to tail, so you might want to move this R vector over so that its tail coincides with the tail of the force vector, and then look at this angle. This angle in this particular case is 90 degrees. In scenario B, you have to be a little more careful. If I move vector A and drop it off over here, I can see that the angle between the force vector and the position vector is going to be 50 degrees. Doing the calculations in this manner, you will find that the torque in scenario A has a magnitude of 12 Newton meters. In scenario B, it has a magnitude of 13.789. In scenario C, it has a magnitude of 10.5. And scenario D, it has a magnitude of 13.789. You may have noticed that some of the torques are negative. Here I'm really not calculating the magnitude, but instead the direction. So I'm using the right-hand rule. So for each one of these cases, if you want to know whether the torque is positive or negative, you'll have to use the right-hand rule. There are different flavors of the right-hand rule. You should decide which one you like. Remember, for one method, you can point your index finger in the direction of R, point your middle finger in the direction of F, and then stick out your thumb. If your thumb points into the page, we consider that the negative Z direction, so we write the torque as minus 12. If your thumb sticks out of the page towards you, then we consider that the positive Z direction, so we write the torque as positive 13.789. Looking at these numbers, you can see that scenario B and D have exactly the same torque. They're the most effective, and the least effective is probably scenario C. So we have seen that if you want to know how effective forces are at bringing about rotation or angular acceleration, you have to calculate torque. Torque is the thing that tells you how much angular acceleration you will have. To calculate torque, you need to use this formula. At least this is the formula that gives you the magnitude of the force. For the direction, you will have to use the right-hand rule. Now, this is the standard formula. This is the formula you'll see most often in our class, but you should know that this formula is also sometimes written as such. Torque is written as R times F perpendicular. F perpendicular in this context is simply F sine theta, and this quantity is often known as the force arm. So sometimes people define torque as distance times the force arm, and you kind of need to know that when they speak of the force arm, they're talking about this particular combination, F sine theta. Some people also write the same formula like so. It's R perpendicular times F, and this R perpendicular is known as the lever arm. In this case, the lever arm is simply the distance times sine of theta. In case you're wondering where this terminology comes from or why people might want to write torque in this manner, it helps to remember that whenever you have two vectors like R and F, you can always decompose one of them with respect to the other one. So for example, you might be wondering, here's vector F, how much of F is parallel to R and how much of it is perpendicular to R? It turns out this vector F can be written as the sum of two other vectors, F perpendicular and F parallel, where F perpendicular is perpendicular to this other vector R, and F parallel is parallel to this other vector R. We describe this situation by saying that we're decomposing F relative to R. We're using R as our reference direction, and we're looking at the parallel and perpendicular components of F in that reference direction. Of course, here I'm decomposing F relative to R, but you can imagine decomposing R relative to F. So you might say F is going to be my reference direction, and I want to know how much of R is parallel to F and how much of it is perpendicular to F. In that case, I have R parallel. You can see R parallel is pointing in the same direction as F. And then you have R perpendicular, and as you can see, R perpendicular is perpendicular to this line, which represents the direction of F. So if you want, you can just continue using this formula here, RF sine theta, but you will see as you read your book that the force arm and the lever arm are also quite common because they're taking advantage of the fact that one vector can be decomposed relative to another vector. And that's the end of this lecture. Thank you for your attention.